Alright, welcome back. So I would like to go over a few old definitions that we've seen and start introducing some new ideas and ways to look at what we can do graphing. So first definition I want to introduce again is relation. A relation is an association between two quantities. The relationship could be one person wears two shoes. It can be represented in words, equations, in equation form, as ordered pairs, and as a table or graph. We started looking at graphs, and we're going to be continuing to look at graphs. So we're going to look at specific types of graphs, and those are functions. And these functions that we're mostly going to look at in the next few lessons are going to be linear equations. So let's again define function. I know I've started using this term, but now we're going to actually see what it means. A function is a specific type of relation. In which each value of the independent variable, in this case x is typically what's used, the independent variable is x, is associated with exactly one variable or one value of the dependent variable. Typically referred to as y. Or in other words, for every value in the domain there is a unique value in the range. And this brings us to, well, relations or associations between two quantities. This could be prices versus number of items you get. This could be goals scored versus number of shots taken. Any type of relationship. Now, a function is a specific type, like I said, where every x value has one y value. And I will go ahead and define domain and range. That's mostly what we're going to talk about the rest of this lesson. But I just want to say that all functions are relations. But not all relations are functions. We'd represent this as a Venn diagram of function. Here's all the functions. All the functions reside inside there. But where are relations? Well, a relation is a bigger field, and it encompasses all functions. So I could have a relation that's not a function, but I have a function, and it's definitely a relation. We'll come back to functions and relations later. I'll post another video about it. First, I would like us to talk about domains and ranges. So let's first define these terms. What is a domain? A domain is the set of all possible values of the independent variable. All your x values in a relation. Now I know I have defined this according to relation, and that is acceptable because all functions are relations, so this applies to functions. Domains are the x values. So what is range? Range is slightly longer in that it is the set of all possible values for the dependent variable. Why? And it goes a little further just to say that as the independent variable takes on all possible values of the range, or of the domain. All possible So the domain is x values, the range is y values for all possible x values. So think of it, of all my possible x values, I have to have a number that matches the range. If I have an x value without a corresponding y, it's not correct. All right. I'm going to start a new piece of paper. And we're just going to talk about different ways we can express and write the domains and range. This is going to be a little lengthy, but you know what? It'll be worth it. Ways to express domain and range. The first way is in words. So I could say, in writing, I could state that the domain and this would be defined as explained in words. The domain is all real numbers between 0 and 10. Inclusive. That means all my x values can be 0 all the way up to 10, and it can be equal to 0 or it can be equal to 10. And I would say the range is the set, is all real numbers is a set of all real numbers greater than 20. And just as a refresher, because I know it's been a while, I'm going to skip over here quickly and I'm just going to draw a little Venn diagram. Hey, why not? What's a real number? Real numbers. We did this at the beginning. It shouldn't be familiar. Let me just focus this again just to make sure. All right. So, you can have rational or irrational numbers. So what is a real number? A real number is any number. It could be -2. It could be a fraction or a decimal, -8.16. It could be 0. It could be the square root of a number that's irrational, square root of 2. It could be a representative of a number. Any number like that could be a real number. And then we break it down into irrational and rational. Let's look at irrational first. Irrational. It could be a number that doesn't give a definitive distinct number. And this would be irrational. I'm going to work slightly backwards so I have enough space. So we have a big circle of rational, but yeah, let's do that. A rational number is a fraction, is a decimal. Those would be examples. Anything that gives you a definitive point, that doesn't continue on like a repeating. Now we can break rational numbers into subsets. It could be broken down into integers. -1, 0, 1, continuing on. We could break integers into whole numbers. 0, 1, 2, dot, dot, dot. And we can break whole numbers into natural or counting numbers. 1, 2, 3, dot, dot, dot. So, inside rational numbers, we have all of these things that are their own subsets. And inside that, you have natural, whole encompass natural. There we go. And these are all real numbers. Everything in the circle is a real number. Some of them are rational, some of them are irrational. They fall into one of those two categories. And we have integers, whole, and natural numbers. So we're looking at any possible numbers, what we're looking at when we talk about real numbers. I will post this as page 2A on the 14th of May, 2020's notes of the Foundations of Math and Pre-Calculus 10. Okay, back to the notes. Wonderful, great. After words, we can express it as number lines. Number lines. It's just explained using number lines. So let's look at the same examples. Let's look at the domain. I might do some pen switcherooing. I need a straight edge, make this all nice and pretty, a couple of colors. So, domain. Let's look at the domain. Negative numbers continuing that way. Positive numbers continuing this way. And so on, not spaced properly, but it's there, they're real. Okay, the domain. So the domain is all numbers, all real numbers between 0 and 10 inclusive. Between 0 and 10 inclusive. Now inclusive tells us that includes 0. How do we represent that? We represent include. Oops, that meant to be blue. That's okay. Closed dot. A closed dot or a solid circle. I guess it's not a closed dot, a filled dot. Indicates the points are included. So this would mean all numbers between 0 and 10 inclusive. And you do the dots and you show where the numbers are. I'm going to draw a line, da, 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 da. Beautiful blue line. There we go. 0 to 10. That's what we have. Now, what would the range look like? Do 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 do. Okay. The range. The range. The thing about this pen is I need to press more hard. It makes my hand tired. All right. The range we've sent up here is the range is the set of all real numbers greater than 20. All right, so I'm going to do 0 down here, 10, 20, 30. There we go. All right. all numbers greater than 20. So how do we represent that? Well, we're going to use an open circle. An open circle indicates the number isn't included. So, in this case, the set of all real numbers greater than 20. So it tells us that, okay, 20 is our limit, but we're never actually going to be at 20. We're going to approach 20 and closer to 20, and it's all numbers greater than. Well, 10 is not greater than. We'd have to go this way. Greater than. And we'd have to put an arrow because we're not setting an upper limit. In this case, we set a distinct limit between 0 and 10. All numbers greater than 20. Let's say I talked the other day about discrete as well. So let's say we had a situation where we were working with discrete numbers. If we had discrete numbers, we take our number line, da-da, do-do-do-do, do-do-do-do, we have 0 here. Let's say -2, -6, +5. And let's say at these spots we had a specific number. Let's say, okay, I took a point at number 6, -6, -2, and 5. And I left out other numbers that were not in the list, a discrete list. Oh, man. There we go. Words, number lines. There are 2 more ways. This is actually going much more quickly than I expected it to. Oh no, 3 more ways. I miscounted. Silly me. I'm going to try to fit this in here. So we can have word notation, number line notation, and we can have what's called list notation. And it's just what it says. It's listing the numbers. And this is good for small sets of discrete numbers. Good. 4. Small sets of discrete numbers, of discrete data. This would look like if I have an example, this can be different from all the ones above. The relation discrete data is not a function necessarily. Points 0, 0, 1, 5, 3, 7, and 5, 7 have the domain of the x values in the ordered pairs, the first numbers, 0, 1, 3, and 5. 0, 1, 3, 5. And the range of, take the distinct numbers, you don't need to be repetitive, so 0, 5, 7, 7. So the y value is the range. The second one in an ordered pair is 0, 5, 7, 7. I don't need to write 2 sevens because 7 is the same as 7. Include each number one time. That would be list notation. I'm gonna get a big stretch here. Oh, sorry. Okay, 3. We're still attending Foundations of Math Pre-Cal 10. It's still the 14th of May, 2020. Okay, now this next one is called set notation. This is what we should be using the most. Set notation. This is the formal mathematical way to state domain and range. And it looks like something specific. So, I'm going to build a little chart, set notation, and what it means. Oh, actually, how do I want to do this? Don't write that down yet. I'm going to define a few things. There's a few symbols that are used in this that are critical. So let's just set out curly brackets. Are used for a set. Oops. We're going to see this solid bar, just a vertical line, and this means such that. So if I put a vertical bar there, if I put then such that, then you have this kind of smooth E. It's kind of the best way to describe it, and it means is an element of. So it's contained within, it's part of something greater. Now I'm going to set up what the set notation looks like. And define by what it means. Let's make this nice little table. We have our domain. And I can say that the domain is the set of values x such that x is less than or equal to 10 and x is an element of the set of real numbers. Curly bracket tells you, whoa, pay attention, this is going to define something. It's important. Okay, what it means. What does it mean? So the statement reads this, if you were to write it in words. The set of values of x and my x is the same, it doesn't matter. The set of values of x, the bar means such that, such that x is less than or equal to 10. And x is an element of x is an element of the big R means all real numbers. And this can be written out nicely like that or in slightly other ways. So that brings us, that's the domain. Let's put a little red box around that. Domain. Why am I putting a red box around it? I don't really know. So we can see where it is. Let's break out the range. Hey, I put a red box around domain, might as well put it around range. So exciting, the life I lead. Take a sip of my drink. Okay. Written a lot today, getting all my notes ready for this class for chemistry. My hand is tired. Alright. Range. Well, range is the set of values y. My curly brackets are always a little wonky. Do them as best you can. Just don't make them look like square brackets or regular parentheses. You need to have a distinct curly bracket shape. So the set of values of y such that y is greater than 20. And y is an element of all real numbers. Look at that. Nice, simple. Once you get used to seeing it, you know what it means. Just like when you're driving, you see a square sign with black lettering that's white background, you know that's a speed sign. Or if you see a yellow sign with black lettering, that's a warning you of something that's changing. A green sign, usually with white lettering, is a direction, guidance sign. You get used to seeing that. Okay, range is defined as, what does this mean? It is the set of values of y. So just the parenthesis, the open bracket, curly bracket, and the y is all of this. Such that y is greater than 20. Oh, there's more. And y is an element of the big R means all real numbers. That's the thing about math and chemistry and that sort of stuff and physics. You can represent a lot of information in short equations and different notations, as you get used to it, becomes more easy. Now, one last one. Interval notation. Interval notation. Interval notation is defined as the use of different brackets for each interval. This isn't a definition I like in words, but when we see in action, it means something. It's a way you can essentially take something on a number line and adapt it to an interval notation. All right, so the types of brackets we will use here are square brackets. Square brackets. And square brackets represent the end number. Represent that the end number is included. Okay, this is compared to a parenthesis. Parentheses. I'm just PARENTHESES. Parentheses. I couldn't remember if that fourth letter was an E or an A. Parentheses. You know, English, tough language, different sounds and letters depending on what they're next to. Changing the way words like trough and dough don't rhyme. And they're end nearly the identical way. Parentheses. What do parentheses mean? Well, they represent the numbers included. Is not included. So, interval notation. And then how it reads, what it means. The domain. Square bracket 0, 10 closed square bracket. How does it read? It reads as all numbers. All numbers between 0 and 10 inclusive. all real numbers between 0 and 10 inclusive. The range. Parenthesis 20, comma, infinity, close parenthesis. Anytime you use an infinity sign, it means it's going to go and there's no set endpoint. And because there's no endpoint, you can't include a specific number, so you always have to use a parenthesis following an infinity. So it reads all real numbers. Greater than 20. There we go. Now I want us to practice working on it. So I'm going to give us a few examples and I want us to work through them and give us definitions of domain and range using the words, a number line, interval, and set notation. Let's start on another piece of paper.